Okay, I want to start today with a little pop quiz. No pressure, but if I asked you for the value of pi right now, what's the first thing that comes to mind?
I mean, for most people, it's going to be 3.14.
Right.
If you're maybe an engineer or you're trying to show off a bit, you might go 3.14159. Or, if you remember middle school math class, you'd probably hit me with the fraction 22 over 7.
Exactly, 227. That's the classic. It's the one everyone learns because it's just so easy to remember. But looking at the sources we've got in front of us today, it turns out 227 is, well, it's sort of amateur hour.
It is. It's a useful tool, but it's a blunt one
Yeah.
because there's this magic fraction that is just so much better. It's 355 over 113.
355 divided by 113. That sounds completely random, like someone just, mashed the number pad on their phone.
It really does look random, but it is shockingly powerful. I mean, think about it this way. 227 gets you 2 decimal places. This one, 355113, is accurate to 6.
6 decimal places.
6. And here's the kicker. This is the fact that jumped out at me from the notes. To get a fraction that is any more accurate than that, you would need a denominator of something like 30,000.
Whoa. So it's this weird little sweet spot on the number line, a tiny packet of information that holds a massive amount of accuracy.
Exactly. It's called the Milieu approximation. But look, we're not just doing trivia on pi today. That number, it's just the hook.
Right. And that's really the mission for this deep dive. We are going to take that idea, the idea that a certain kind of fraction can capture complexity better than anything else, and we're going to trace it from abstract math all the way into the physical blueprints of the device you're listening to this on right now.
We're going from 355 over 113 straight to a circuit board.
And this is the part that, I had to read it twice, because usually you think of engineering as you build a machine and then you use math to figure out what it does.
Right. Analysis comes after the fact.
But today we're flipping that script completely.
We are. We're talking about taking a mathematical wish, just a pure abstract function on a piece of paper, and literally compiling it into copper and capacitors.
It's like 3D printing, but for logic. You feed in the math and the hardware blueprint comes out.
That's a great way to put it, yeah. We're digging into a stack of papers here on rational approximation, something called the Vyskova-Tov algorithm, and the synthesis of RLC networks.
Okay, that sounds incredibly dense. Rational approximation sounds like a class I'd fall asleep in. But the core idea is it's surprisingly simple. It all starts with a flashlight.
The flashlight in the dark room. Yeah, this is the analogy the source material uses to explain why we even need this new type of math.
So set the scene for us. Traditionally, if an engineer wants to approximate some complicated curve, how do they do it?
The standard tool, the hammer in every toolbox, is the Taylor series. If you took calculus, you definitely remember this. You take a complex function and you break it down into this long chain of simple terms. A number plus an x term plus an x squared term and so on.
It's just a sum of polynomials. You're adding simple shapes to copy a complex one.
Correct. And the Taylor series is fantastic. Locally, it's like standing in a pitch black room and turning on a flashlight. You can see the floor right in front of your feet perfectly. The detail is incredible.
But the further you look away from that spot,
the dimmer it gets. And it's not just dimmer, it's wrong. If you try to use that math to predict what's happening on the other side of the room, it fails completely.
and there's a hard limit, isn't there?
Yeah.
It's not just that it gets blurry. It actually hits a wall.
A radius of convergence. And this is where the physics comes in. Because in the real world, things blow up.
Literally.
Sometimes literally, yeah. But also mathematically. We call them poles or singularities. Think of microphone feedback. That screech that goes to maximum volume instantly. Or a phase transition like water suddenly flashing to steam. The numbers, they just shoot to infinity.
And that's the problem with the Taylor series. Because I would just assume if I added enough terms, an infinite series, I could describe anything.
That's the logical intuition, but it's wrong. And here's why. A Taylor series is just adding finite things together. A plus B plus C. You can do that all day long. You will never, ever reach infinity. A polynomial is too safe. It's too well behaved to model a catastrophe.
So if you're trying to model a circuit that might resonate and blow up, the Taylor series is basically blind to that danger.
It won't see the cliff until you're already over it. It just physically cannot model that vertical line going up to infinity.
So we need a better flashlight, something that can see the whole room, including the dangerous parts.
Enter the hero of our story, the Padé approximant.
And looking at the math, the difference is so simple. A Taylor series is a sum. A Padé approximant is a fraction.
It's a ratio. One polynomial divided by another, p of x over q of x.
Why does just drawing a line and putting something on the bottom change the game so much?
Because of the power of division. In math, what happens when the denominator, the bottom number hits 0?
Well, the whole thing shoots up to infinity. You get an error on your calculator.
Precisely. Because the Padé approximant has a denominator, it can model infinity. It has a built-in self-destruct button, a way to simulate those blow-ups. When the denominator hits 0, the function creates a pole.
It's like a radar for instability.
It is. It extends the map. Instead of just seeing the little patch of floor at your feet, you start to see the whole system. The walls, the ceiling, and the spikes.
Which brings us back to our friend 355 over 113. That's not just some random fraction. It's a Padé approximant for pi.
It is. It's the best rational approximation you can get with numbers of that size.
But that begs the question. How do you find these magic numbers? You don't just sit there guessing, right, let's try 354. No, how about 355?
No, that would take forever. There's a system. The sources call it an engine for generating these things.
The Vyskevitov algorithm.
Yes.
It sounds like something out of a Sky movie, the Vyskevitov protocol.
Yeah.
But it's really just a method of, recursive division?
It's a game you play with the numbers. Let's say you have a messy infinite series, like the one for pi. Vyskevitov says, Step 1. Divide 1 by your series. See what you're left with.
The remainder.
The remainder. Then you take that remainder, you flip it upside down, invert it, and you divide again. And you just keep doing that.
So you're just drilling down, invert, divide, extract. Invert, divide, extract.
Exactly. And as you do this, you're building what's called a continued fraction. It looks like a fraction inside a fraction, just cascading down the page.
And if we feed the series for pi into this engine, what pops out?
Well, if you stop the algorithm at step 1, you get 227.
Okay, so that's where that comes from. It's the first roughest cut.
Right. If you stop at step 2, you get 333 over 106.
Which is a little better.
A little better. But then you hit step 3, and all of a sudden the algorithm spits out 355 over 113. And the error just plummets from about 0.0000008%.
That is a massive jump in efficiency. It's like the algorithm just found a universal shortcut.
It distilled the essence of pi into the most efficient ratio possible at that scale. That's the power of this method.
I noticed the notes also mention a Lord Broncker.
Yes, from the 1600s, he found this generalized continued fraction for pi that's just beautiful. It's 4 divided by 1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared.
Wait, it's just the odd numbers squared. 1, 3, 5, 7.
Oh, the odd numbers squared, cascading forever. It's this deep hidden link between pi and the odd integers.
That feels profound. But okay, before we get lost in the philosophy of it all, we promised to connect this to the real world.
Right, the from infinity to copper part.
Yeah. Because so far, this is great for a math textbook, but how does this Vyskevitov thing help me build a 5G tower?
Well, to get that, we have to look at how engineers usually work. We call it analysis. You build a circuit, you solder some resistors and capacitors together, then you use math, like Kirchhoff's laws, to figure out what you just built.
So you start with the hardware, you derive the equation.
And here's the funny thing. When you derive that equation, the transfer function, it almost always turns out to be a rational function, a ratio of polynomials.
Okay, so nature just likes ratios. Circuits naturally behave like these fractions.
Exactly. So about 100 years ago, some very clever engineers started asking the reverse question. If a circuit creates a rational function, can a rational function create a circuit?
Hold on, you mean doing the math first? As in, I want a filter that does exactly this. Write the equation, and then have the equation tell you how to build it.
That is exactly it. It's called network synthesis. It's the inverse path.
That sounds like magic, but there have to be rules. I can't just write output equals infinity and build a perpetual motion machine.
You're right. You are constrained by physics. The function you dream up has to be what we call a positive real function, or a PRF.
Okay, break that down. What does positive real mean in the workshop?
2 main things. First, stability. The poles, those blow-up points, they have to be in what's called the left half plane.
Which means they dampen out over time instead of exploding.
Right. You don't want your radio to turn into a bomb. The second rule is passivity. The function has to describe a circuit that can dissipate energy, like a resistor getting warm, or store it, like a capacitor. But it cannot create energy.
So as long as I don't violate the laws of thermodynamics, I can compile my math into a circuit.
Yes. And the way we do it is by using our old friend, The Vyskov algorithm.
The same division game we use for pi.
The exact same game. But in electronics, we call it Cauer synthesis.
All right, walk me through this. I have a function, this ugly ratio of polynomials. How do I turn it into parts I can actually hold?
We use what the source calls the translation dictionary. I want you to picture a ladder. Two long parallel wires with components connecting them like rungs. A ladder network.
Okay, got it. A ladder. Top rail, bottom rail.
Now let's take the example from the slides. Our target function is 16s squared plus 130s plus 1 divided by 8s plus 1.
It's just a bunch of algebra homework. I wouldn't know where to be.
But watch. We apply Vyskov. Step 1. You divide the top by the bottom. The algebra works out and it extracts a constant term. In this case, the number 1.
Okay, so we pulled out a 1. What is 1 in the physical world?
In Cauer synthesis, when you pull out a constant in the series position, you add a resistor. Specifically, a 1 ohm resistor.
So I just solder a 1 ohm resistor onto the top wire of the ladder.
You do. That's your first part. Now you have a remainder from that division. Step 2. Invert that remainder and divide again.
Just like with pi. You flip it and repeat.
Exactly. This time, when you divide, you extract a term with an S in it, specifically HS.
An S term. It's usually related to frequency. What component is that?
When you're in this inverted or shunt position across the ladder, an S term is a capacitor. So you connect an 8 farad capacitor from the top wire down to the bottom wire. It's the first rung of your ladder.
So we have a resistor in series, then a capacitor as a rung going to ground.
Step 3, you invert what's left and divide again. This time you extract the number 16.
Another constant.
Yeah.
So another resistor.
Yes. A 16 ohm resistor in series right after the capacitor.
And the final remainder.
It simplifies down to a term that represents a 0.041 farad capacitor as the final rung.
That is just why we literally just walked down the equation.
Yeah.
Divide resistor, invert and divide capacitor, invert and divide resistor.
And here's the real aha moment. Think about electricity flowing through that circuit you just built. It hits the first resistor, some voltage drops, it gets to the capacitor, some current splits off, then it hits the next resistor.
The electricity is physically performing the steps of the division.
The circuit is the algorithm. The electrons flowing down that ladder are physically calculating the continued fraction in real time. This is what we mean by Padé in copper.
It completely changes how you look at a circuit board. I mean, I usually just see a maze of green and gold lines. But you're saying it's a frozen calculation.
It is. The topology, the physical shape of that ladder, is the math made manifest. And this method, Cauer synthesis, it's foundational. But I should say it's not the only way. The notes also highlight Darlington's method as the real gold standard.
Darlington. What did he change?
He looked at these Cauer ladders and basically said, too many resistors.
And why is that a problem?
Resistors create heat. They create noise. In really sensitive communications like deep space radio, you can't afford that noise. It drowns out the signal. Darlington proved that you could build any of these functions using only lossless parts inductors and capacitors with just one single resistor at the very end.
So you do all the complex shaping of the signal with the parts that don't waste energy, and then you just dump the power in one controlled spot at the end.
Exactly. It's pure elegance, ultimate efficiency. And it's all based on the same fundamental math.
It feels like a grand unification of sorts, doesn't it?
It really is. I mean, the sources lay out the whole chain. You start with a power series. You run it through Vyskov. That gives you a continued fraction, which is a Padé function, which you synthesize with Cauer into a physical RLC ladder.
The same structure that tells us 355113 is a great approximation for pi is the exact same structure that lets your phone filter out all the noise so it can get a clean 5G signal.
It's this hidden architecture in the universe. We're not inventing these efficiencies so much as we're discovering them. It turns out a ratio is just a deeper, more powerful way to describe reality than a simple sum.
It makes you wonder what else is out there.
What do you mean by that?
Well, if a simple RLC circuit is just a physical calculator for a continued fraction, what other parts of our physical reality are just mathematical algorithms running in hardware?
That's the big question, isn't it? Is the universe just running Vyskovitov's algorithm on some grand scale? Are atoms and planetary orbits just the hardware implementation of some deeper mathematical truth?
I think that's a rabbit hole for another day. My brain is pretty full. But for now, I am never going to look at a circuit board the same way again.
No, it's not just wires. It's long division captured in metal.
And remember, next time someone asks you for pi, don't give them 227.
355 over 113. It's the only way to fly.
Thanks for listening to The Deep Dive. We'll
Bye-bye.
catch you on the next one.